Okay, I think it's working. Welcome to the review, and it's exactly 8:15. Feeling good about that. I'm Mrs. Staub, and we're going to talk about atomic theory and periodic trends. I got to switch between documents a little bit here. I think it's working. I want to check it with the backup on my iPad, but right now I'm just going to go with it. Let's see. Okay, it looks like it's working. I'm going to try and get a periodic table up here so we can talk about the first question. And I want to get the view up. Okay. Oh, come on, periodic table. Oh, it's working. Awesome. Okay. I know this isn't good TV right here, but I'm just trying to get all my screens open. Okay. All right, we're starting with how do you write shorthand electron configurations. What I'm trying to still get up is a periodic table, but it's not being that friendliest. Okay, this should work. Put a light on it, that would be awesome. Sorry, I would have done this at a time, but my little girl just went to bed, so you're going to have to deal with me. I'm trying to find my paint program. Oh, good. Okay, we're doing good now. Let's see if I can share my screen. Okay. All right, I believe you can see my screen now, which is awesome. Okay, our first question is on how do you do electron configurations when there's shorthand? So we'll just start with kind of like a big one down here. I don't know, like calcium might be a good one. Let's see if I get my paint marker here. Calcium. So when we think about calcium, let's go red. Now calcium's right here, and to do the longhand electron configuration, I have to start at the very top and start with 1s2, 2s2, and those sort of things. So what I'm going to do is start the shorthand configuration, which means go to the nearest noble gas. So if I back up here just to argon, which is my nearest noble gas, it's got to be something below it. Now calcium is number 20 and argon is number 18, so that's pretty close. So the shorthand configuration for calcium would be argon, and you write it just like that. And you put in those brackets, and that tells scientists do all of the electron configuration for argon, and then add on where I would be right here with potassium, 2, 3, 4. So that would be 4s2 to get to calcium. So let's try a different one then. Something maybe a little bit trickier, like rhodium. For rhodium, I've got to once again backtrack until I can get to the nearest noble gas. Now they pick noble gases because it has a full outer ring. It's got that energy level filled, so it's complete, so it's a good one to go with. So if I want to do it for rhodium, number 45, I would write krypton in the brackets because it's my nearest noble gas, and then add on the rest. So this down here is row 5, so that'd be 5s2 And then I'd be going to 4D, 1, 2, 3, 4, 5, 47. And that would be the electron configuration for number 45, rhodium. I think that pretty much covers it for that. Okay. The next periodic table out, we're going to set. Okay. Okay. So the next one you might want to look at, and I can show you my screen, we're going to talk about a few Jeopardy questions. So let's take a look at the Jeopardy questions. Oh, let me screen share with you here. Oh, that's not the screen. This one. Okay, so here's the document, and we're going to talk about this question. This is from the first row, 500. The following transitions on the Bohr hydrogen atom. The blank transition results in the emission of the highest energy photon. Okay, the highest energy photon in the Bohr model would be one where you have the biggest jump. So to recap what the Bohr model is, the Bohr model basically will tell you that you got energy rings, you can see down there, which he calls orbits. And really in real life, it would be called orbitals, so they would jump from bubble to bubble. But here we're going to talk about orbits in the Bohr model. So in the Bohr model, you might have an electron that lives here, which is the ground state, and that's where he happens to live. It's in the second energy level, so he would be an electron in the second row of the periodic table. Now, if you give him electricity or some sort of heat or something, he could absorb energy and move outward. When he moves outward, that's when he absorbs energy. He takes it in. Now that electron isn't stable out there, that's called his excited state. And in order to release his energy, he has to release his energy, and he can go all the way back down if he wanted to. But the energy that he releases will be in the form of colored light. Now, if you make a big jump such as this, that may be something like a green color, I'd have to say. If you make a different jump, that's more energy levels, maybe this jump here, from here all the way down, that will be more of a blue light. So the bigger the jump inward into towards the nucleus, the bluer the light, the more purple the light. So if we go back to this question and think about it, the most light, the highest energy photon being just a packet of light, would be the biggest jump outward to the biggest jump inward. So let's go back to our question here. The biggest jump from the outer to the inner would be this B. That would be your answer, B. Because you're going from energy level 6 all the way to energy level 1. That's a big jump. That's a highest energy jump. Okay, next one. What is the number of electrons in the outermost energy level of a europium atom? All right, so we got to go to our periodic table and find europium. The big question about this is about energy level. That's the key word right there. So I'm going to highlight that. Energy level. We're finding the outermost energy level. So here's our periodic table. I can make this too big. Europium is EU. He's down here. I'll be in yellow. Well, you can't see yellow at all. I can barely see it. Okay, europium is right down here. So if I was to do a shorthand electron configuration, I think that might be like the easiest way to go. So let's back him up a little bit farther, and I'd see I've got xenon. Xenon would be my shorthand electron configuration for europium. So I would go xenon, and then I would add on this row. So I'd have to count 1, 2, 3, 4, 5, 6. So this would be 6s2, and then I go to the F block, 4f, 1, 2, 3, 4, 5, 6, 7, 4f7. Now the question asks how many electrons in its highest energy level. The highest energy level for europium is energy level 6, row 6, and he happens to have 2 electrons in his energy level. So the answer to this question is 2, because he has 2 in his 6th energy level. There you go. All right. Next question. In which pair is one on the left larger than the one on the right? Okay, so big one versus one on the right. Got it. This will be hard to kind of note back and forth, but we'll try it. Oh, double screen. Perfect. Okay. Okay. Let's put in a new periodic table here. Boom. That'll work. Okay, so when we're looking at the size of the atom, that's maybe where we should start first. As you go this way, it gets smaller. That's because there are more protons in the center, and protons are stronger than they are alone. And as you go this way, it gets bigger, and that's because you're adding energy levels. You're adding rings or orbitals to it. Okay, so if we take a look at our pairs, I'm looking for the one on the left is larger than the one on the right. So we'll look for on rubidium. The one on the left is smaller. So this isn't a good pair because it has fewer energy levels than rubidium. So that A is not a good answer. If I look for sulfur, sulfur versus magnesium, sulfur is the smaller one. And that's not a good answer to this question because sulfur is on the left and we want the larger one on the left. Next one would be bromine. Bromine with iodine. The one on the left is bigger than the one on the right. Wait, the one on the left is smaller than the one on the right, so that's not a good match. Last but not least, we've got helium and potassium. This one here is a good match, I believe. Potassium has many more energy levels than helium. It has a lot more electrons than helium. So potassium is the big atom here, and helium is the smaller atom. So that would be a good answer to that question. All right. We'll just keep moving right along here to the next question. 27. It says, which is the halogen that is in period 5? Okay, so I'm guessing if you have a question on this one, it's to understand the terms halogen and period 5. So I'm going to write over this with green. The halogens are this family right here. The one with fluorine, chlorine, bromine, iodine, they're the halogens. And period means rows. So as you go across, these are the periods or the rows. As you go down, that's called groups or families. Columns are called groups or families. Periods are called the rows. So if I go 1, 2, 3, 4, 5, the halogen that's in the 5th row down would be iodine, and that's why this answer is C. I'm going to highlight them in red because why not, right? Okay. All right. And how does the Heisenberg, make sure I've got no other. Oh, thank you to this person down here at the bottom. Why did you pick the 2 electrons in the S energy level rather than 7 on the F energy level? So I'm going to answer this question right now. 829. I am picking the one with the highest outermost energy level. Outermost means the highest energy level. That means the greatest row. Row 6, this is 6s, and 6 is a bigger number than this F, which was a 4F. Since 6 is bigger than 4, 6 is the highest energy level, so I picked the 2 electrons. Those are the only electrons in the 6th energy level, which is the outermost energy level. All right, going back up. I'm going to try and organize these to put them things together. Heisenberg problem. Okay. Here we go into the next one. 8:30. We're talking about the Heisenberg uncertainty principle. And how does a Heisenberg uncertainty principle and de Broglie equation explain the wave mechanical model? Okay. I'm going to get myself a screen here, I think, because I like to draw. So the Heisenberg uncertainty principle says two things. Well, not two things, really one thing. It says that there's the position and the velocity of an electron, and you can't know both at the exact same time. In order to find the position of an electron, you'd have to shoot it with something, because we can't use a microscope to actually see the electron. So we'd have to get a microscope that was super, super strong, but we don't have that. So it's just like when we want to find anything in the dark, like I use the balloon in the dark and you're trying to find the balloon. The only way to know where the balloon is if you touch it. Well, we can't really touch an electron, but we could shoot it with lasers or other particles. And so when we shoot the electron with lasers or other particles, we can see the position of it. In other words, like, let's say you've got an atom and you shoot particles in there. Where these particles deflect can kind of tell you where this electron is. But when you hit that electron, you have no idea how fast the electron is going. It could be going 90 miles an hour and you hit it, or it could be stopped and you hit it. You can't possibly know both the position and the velocity of an electron at any one time. The more you know about one, the velocity, the less you know about the other, the position, and vice versa. Okay, so why does this even matter? Well, the real reason this matters is because when you're dealing with orbitals, which is the wave mechanical model. The wave mechanical model says things are in orbitals. So here's my p orbitals. What that means is that electron is found here 90% of the time. The other 90% of the time, we don't know where it is because of the Heisenberg uncertainty principle, because we know that we can't always know its position. The more certain we are of its position, the less certain we are of its velocity. So, because we can't know both at the same time, we can't know where the electron is 100% of the time. That's impossible. So, by calculations, they found that the orbitals, they know the electron exists here 90% of the time. And that's how it supports the wave mechanical model. The other question this person had is, how does the de Broglie equation, how does the de Broglie equation support the wave mechanical model? So de Broglie is the guy who came up with the wavelength is proportional to this equation. Wavelength being the lambda, h being Planck's constant. This is the wavelength. M is for mass, and v is for velocity. Okay, so from this equation, we talked about how if you had an electron, electron's mass would be very small, freakishly small. We know Planck's constant is 6.626, you don't have to memorize that, times 10 to the negative 34. That's freakishly small. The velocity is a semi-big number, but not super big. It's big-ish, but not super big. Not compared to how small the mass of an electron is, negative 27. And how small the Planck's constant is, negative 34. The velocity is 10 to the 8th. And all the rest of these are 10 to the negative 27, 10 to the negative 34. You can kind of see there's a big difference between 10 to the 8th and 10 to the negative 34. So really, if we don't think about velocity in this equation, we're taking a really small number divided by a really small number, and basically we're going to get a semi-normal number, a number that we can use. A number in nanometers. Nanometers is a typical wavelength, like red light is 656 nanometers, I believe. I can't remember what the wavelength of the electron was, but I feel like it was in the 20s, like 23 nanometers. I could be wrong on that, but it was ish that. So that's like a normal-ish number, which means that we could actually find the wavelength of electron. That's completely possible and feasible, and we could do it. What this de Broglie equation said is that electrons move in waves. It also proved that everything else moves in waves. But the big thing, the big question we're asking here is, how does it support the wave mechanical model? It says that all electrons move in waves. So why does that matter? Well, remember that if electrons move in waves, here's a wave, or maybe an electron might move in this wave, Or maybe he might move in this wave, or maybe he might move in this wave. You can see that when you put waves together, you can create these bubbles. And this is the start to a p orbital. Now this is me kind of trying to take very complicated things and put it into making sense, but this is the general idea here, that if electrons move in waves, then the regions that they live, they can't live in rings anymore. Rings are orbits, and you can't wave through an orbit. It just doesn't make sense. But you can wave through orbitals. And that's why all those orbitals have those funky shapes, because you can imagine how different waves might overlap each other, and this overlapping waves make the different shapes. So de Broglie's equation gives us the idea that you can't live in rings. You gotta live in orbitals. Okay, let's go back to our screen here. That's not the screen I want. Okay. I am not going to do these ones. I'll put in my time here. Because as you notice, you never had to actually use the de Broglie equation. Like, you didn't have to plug in numbers in the de Broglie equation. To me, that's not all that important, because it just tells you a wavelength of things, and then what do you do with it? To me, it's understanding what that equation was used for. I will give you the equation on the test, but I'm not asking you to actually plug in numbers in there. So I am not going to solve for de Broglie's equation, because you don't actually need to know how to do that. You just have to know why was it important, which we just talked about. There were other, so let's go to this question then. What equations or conversion factors do we need to know? You don't have to memorize any of them, first of all. Second, the equations, I put them all at the top of the test. I also put conversions factors at the top. So the equations that I have at the top are the de Broglie equation, the speed of light, that's the C equals lambda times nu. I have the E equals HV equation. That's the how much energy comes from a wavelength equation. What else do I have up there? I've got constants that are listed, like H, Planck's constant. I have C, the speed of light, listed. I have conversion factors listed up there. Conversion factors I don't expect you to know, like nanometers going to meters. I have megameters going to regular meters. And remember what else I got up there. I have, for a constant, I do have the mass of an electron. I think that's it. I think so. Yeah, I'm pretty sure those are the ones that you need to know. Is there any others? Planck's constant? I think that's about right. I would have to actually look at the test to make sure I got all of them, but I'm feeling pretty confident about that. So that should be good. Okay, calculate frequency next. I'll put this one. Here. Okay, so will we need to know the speed of light and Planck's constant in the equations for frequency and energy? Yes, you will. Put the time here. You'll have to be able to calculate those things, and I will provide all those equations and the constants. So that should be pretty good. Next question is, can you explain how to calculate frequency? Okay, well, there's two kind of ways to calculate frequency, but I can do them for you here. We'll start that now. So, can you explain how to calculate frequency? Okay. I wish this could make it bigger. Oh, there we go. Okay. Okay, so there's two equations that we've got. E equals H times V. In other words, E being energy. This is really fat writing. I have to change that. H being Planck's constant. Wow, that looks terrible. Sorry, I just couldn't deal with it. Let's try it this way. And V being frequency, it's not really V, it's actually nu, but we'll go with V, we'll go for it. The other equation is C equals lambda times frequency. Lambda being your wavelength, and V, or nu, technically being your frequency. And we know C to be the speed of light. So the speed of light I would have to give you is 3 times 10 to the 8th meters per second. I'd also have to give you Planck's constant, which is equal to 6.626 times 10 to the negative 34th joules times seconds. And that's all the numbers that I'd really give you. So if you had to solve for frequency, there's two places that frequency exists. So really you just have to kind of decide, what do they give me and what do I want to find? Like if they tell you, you have red light. And red light has a wavelength of 656 nanometers. Okay, well, and it's asking you what's the frequency. Well, if I have wavelength and I want to find frequency, then I'm going to have to use this equation that's on the right here, where C, or 3 times 10 to the 8th, is equal to the wavelength, 656 nanometers. Now, nanometers is not useful. Wavelength has to be in meters, and that's because the speed of light is in meters. So the wavelength has to be meters. The left and the right of the equal sign have got to be the same units. So I've got to convert these nanometers into meters. I'll just kind of do it right here. 656 nanometers. I've got to get out of nanometers and into meters. And then I can find my frequency. So to do that, I would look at the top of the test, and the top of the test would tell me there's 10 to the 9th nanometers in 1 meter. This gets me out of units of nanometers and into meters, which is what I need. So now, if you look, I've got C equals wavelength times frequency. And then I can solve for frequency. To be honest, my calculator died, and I don't really want to have one here. But if you use the buttons on your calculator, you'll come up with a frequency. The frequency has units of hertz, or per second. Hertz and per second are the exact same thing. Another way to write per second is s to the negative 1, seconds to the negative 1. So that might be one way to find frequency. Another way to find frequency is to say you have red light and it has a set energy of, oh, I feel like I can't even make up a number for this one. Yeah, I can. It gives you a set energy of 6.2 times 10 to the negative 19th joules. That's like a number you might get for energy. So if they give you that energy, then you're going to plug it into 6.2 times 10 to the negative 19 joules equals your Planck's constant, 6.626 times 10 to the negative 34 joules times seconds, times your frequency, which is what you want to solve for. If you check out your units, joules is on the left and joules is on the right, they cancel. And the only way for this frequency and stuff to cancel is if I have per second for my units. Then I would have this be per seconds for my units. Seconds on the top and seconds on the bottom would cancel. Your units on the left will always cancel your units on the right. So make sure to check units. They will never leave you all year. We've got to be careful with that. I hope that is good enough for that person's question. Let's see if they said something below. No. Okay. Okay. Next question. I'm going to take a timeout. Make sure my video is still being happy. Oh, yeah, it's looking pretty good, I think. No, okay. Okay. Next question. All right. Things are looking good. 8:45. Could you explain number 3 for the isotope problems? I love that you guys put the problems in here. Thank you so much. I'm going to type this one out right here, I think. Let's So for any of these questions, we really have that same format where you're going to take the mass and you're multiplied times the percentage. And you're going to add to that the mass and multiply that times the percentage. And then you're going to add to that the mass and multiply that times the percentage. And so on and so forth, however many masses you might have. And in the end, that's going to calculate the average. Now, it's not a pure average, it's a weighted average, but the average mass. And this right here is the atomic mass number. That's the number that's on the periodic table. So in this case, we've got magnesium. So I'm going to plug in the numbers that I've got. The mass is 24.99 for the first isotope. And it said it has a percent abundance of 10.13. So I'm going to put that into percentage form. In other words, divided by 100. So 10.13 turns to 0.1013. And I'm going to add that to the next isotope, which has a mass of 23.99. I'm going to multiply that by its mass, which I do not know, so I'm going to call X in this case. And I'll add that to my next mass. My last mass is 25.98. Oops. I'm going to multiply that by, here I might call it Y, because I also don't know its percentage. But Y doesn't really help me, because then I have two separate variables. But I do know that all the percentages have to add up to 100%. Or, since I'm going in decimal form, they have to add up to 1. So I'm going to do 1 minus 0.1013, my first percentage, and also subtract from that X. Because really, if I had 100, my 10% plus my X percent plus my Y percent, which is what I just put in here, would add up to 1. So I just manipulated that Y in order to equal out to what Y would be. 100% minus the 10% minus X percent. And whatever we have then is going to get me to this percentage here. And that's equal to the average atomic mass. In other words, I look for magnesium on the periodic table, and he is 24.305 from my memory. Feeling pretty good about that. I'm not even going to check. There we go. And that number on the periodic table comes in AMUs, just like the rest of these masses. So at this point, I just got to do some fancy math in my calculator. And I'm going to trust you to do that also because, like I said, my calculator died, unfortunately. I could use my cell phone, but I am not as nifty at that as you guys happen to be. I'm going to trust that these are your algebra skills and that you can do it. This would be an algebra time that I would expect you to know. If this math algebra skills is scaring you, please note that this is a quarter point to get the right number. You just have to, in the end, write a number down. So there you have it. I hope that helped. Okay. Next question, heat free. Was Bohr the first to discover the positively charged center as opposed to electrons swimming in a sea of positive charge? Is it good? Like, I'm not even here. You can see me. Hello. So this question is about Bohr. Was he the first one to discover the nucleus, really, is what they're asking. The positively charged center. He is not the first to discover the nucleus. The first guy to discover the nucleus was Rutherford. And Rutherford was the guy who, do you remember doing that marble thing? So you had those marbles and you shot them underneath the boards and you tried to figure out what was underneath those boards, those pieces of wood that I taped down there. Well, that was Rutherford's model. He shot alpha particles at a piece of gold foil. And he saw that some of them came bouncing back at him, which is what happened when you rolled the marble. Sometimes you roll the marble and they come back at you. And when you did that, you knew that you hit something. Well, Bohr thought the same thing. Not Bohr, Rutherford. Rutherford thought the same thing. So when he rolled a marble or an alpha particle, it hit something in the center and bounced back at him. So that something in the center had to be positive because he shot positive stuff at it. And that something in the center had to be really dense. And that's how he discovered the nucleus. So Rutherford was the guy who discovered the nucleus. Let's go back to the sheet. How does ionization energy relate to atomic radius? I'm sneaking in here, person. So ionization energy and atomic radius are definitely related. I'm going to draw a picture with this one. Okay. So if you happen to have an atom, I could draw the orbitals, but to me bubbles are kind of hard to see because you overlap all the bubbles, it just kind of looks like a scribble. So we'll go this way. So if you happen to have an atom that's this big, or if you happen to have an atom that might be this big, the part in the center here is our positive nucleus where the protons are living, and I've got an outer electron. Now we were talking about in class first ionization energy. That means the outermost energy, the outermost electron. How much energy does it take to remove this outermost electron? You can see that the distance on this one on the left between the positive nucleus and the electron is pretty small. You can have a pretty good hold on it. This nucleus can hold onto that electron pretty good. It's like two magnets. They're close to each other. They can hold things easier. While here, it's many energy levels out, many orbits out or orbitals out, and that distance is greater. So this nucleus can't hold the electron as much. So this atom is bigger and will have a lower ionization energy. Ionization energy is the amount of energy needed to remove an outer electron. Since this electron is so far away from the nucleus, it's not being held in very tightly by the protons or the positive center. So therefore, it'll be easy for the electron to go away. Easy for the electron to move out, low ionization energy. This electron over here is held in tightly by that positive nucleus because it's so close. That's why it has a high ionization energy. It's hard to remove that electron. Let me recap that. This electron is so close to the nucleus that it's hard to remove that electron. Because of that, it takes a lot of energy to do it, so you have a high ionization energy. We have to know what atomic emission spectrum is. Yes. The atomic emission spectrum is what Bohr's model was all about. So if you go back to your article here, these are examples of atomic emission spectrums. So you can see that mercury, this is his atomic emission. This is lithiums and cadmiums and strontiums and calciums and sodiums. Each atom has a specific atomic spectra. And that's exactly why Bohr knew that each element had to be different in some way to produce all these different colors. The atomic spectrum are like a fingerprint for each element. And they're a fingerprint because each element is different. Each element is different because they have different kinds of rings, meaning different spaces between the rings. They have a different set of number of electrons, so they have different jumps that they would possibly make. So that's the atomic emission spectrum. You should know what it is. I got to the end of my questions. I'll hang out here and see if anybody asks me something else. I might go get ice cream, you know. That's what I think. I'll wait and see if somebody sends me some questions. Ooh. We'll check the email, see if somebody sent me something. I see you guys are studying early. That's good. You should go to bed too. Go to bed early. That would be nice. I know you never do, but you should try it. It's quite lovely. If you, oh, here's one. If you were looking at the the Jeopardy game, the Jeopardy game is in PowerPoint, and that's where all like the animations and stuff are functioning well. And I put it into Google, and it didn't function all that well, so I'm sorry about that. I hope that you can still kind of figure things out from there. What was the plum model? I'm going to add in that this is the plum pudding model. 854. The plum pudding model is the same thing as the chocolate chip cookie model. Which was set in by Thomson. There you go. Are you still seeing me? I don't know what I'm showing you right now. Yep, you're just watching me. There you go. I'm gonna check my phone because that's what you would be doing right now, right? Totally. Or keep watching the screen. You got 4 more minutes, lovely folks, and then I'm gonna close shop because you should go to bed too. Yeah, you're right. I'm not going to bed quite yet, but I'd like to. That'd be lovely. I know, isn't it fun to watch some new text? It's terrible, right? I should make you guys sign in because on this document, all I see is like, you know, you're anonymous. I don't know who you are. It's kind of creepy. Not really that creepy, but. It would just be fun to know like how many different people looked. Yeah. It'd be nice. This is my house. Welcome to my house. This is my den, office, thing. And I introduced you to my dogs, but they're in the living room, and the cats came and went, so there's really nobody here to show you too. But I promise I'd be here till 9, so I will be here till 9. Doing a whole lot of nothing. Give you a tour of my house. That's kind of weird. So I think. Oh, I need to do that too. Oh, God. I'll do that right now. Nobody's asking questions. Well, folks, it has been lovely speaking to you through the interweb. I think this is where I bid you adieu until you're going to go to sleep. And I will see you tomorrow. So good luck. Good night.